So in this lecture, we need to move to the fundamentals of energy transport. We're still covering some of the basics that you're going to need in that course before we jump into more details about the course content. So we still, that's maybe lecture number 3. I will call that part 2. Part 1, we did cover the units, and we did learn that we have SI unit system. We have the British system, and we have the that's British gravitational unit, BGU, right? And we have the English system, and we did explain the difference between each one of these systems. We also covered what we call it the dimensions, system of dimensions, or dimension system. And we know that we have MLT system, and we have the FLT system. Then the third topic that we covered in part 1 lecture was actually the engineering prefix. That's the way of writing numbers using the 10 to the power, and we give a list of the different values or different names that we can use in writing numbers. So now we're going to move to the fundamentals of energy transport. This is a very common name here, and the word energy can be actually maybe simplified by the word heat, and the word transport is more generic for the word transfer. So this is the basics that we need to be aware of before we dive deeply into more complicated issues. So what do we mean by energy transfer or energy transport or heat transfer? I will talk about the energy move over time. So always everything is dynamic. So the time is always involved in the thermal hydraulics. So usually when we say that heat transfer, I mean that rate of heat transfer. Okay, which we can simplify as heat transfer. But keep in mind that everything is rated relative to the time. So heat is a form of energy that if I pick the SI unit to be the standard system of units we are using, so heat has a unit of joule. So you guys recall work, heat, moment, and so on. It's all joule. Then I say rate, which means that the time rate, which is we are dividing by time. So we're going to end up having the rate of heat transfer, or the heat transfer that you need to calculate. It's going to come in the unit of watts, which is joule per second, right? Which we call that the watts. And to give that a symbol that we're going to use along the course, that's going to be always the symbol Q small. So Q small is presenting the rate of heat transfer, or in simple language, it's the heat transfer. And this will have the units of watts. Sometimes we extract other calculation out of that heat transfer rate. For example, we sometimes need to calculate the heat transfer rate per unit length. So heat transfer or rate of heat transfer per unit length. So up to here, the rate of heat transfer has the same unit as watts. Now I'm calculating that per unit length, which means that the units of that term is going to be actually watt per meter. And as a symbol, we use actually the same Q, but we put actually dash over the face. So Q dash is presenting the rate of heat transfer per unit length. And that could be very useful in nuclear application, because we look to the fill rod, which has a 10 feet height, maybe 12 feet height, and we would like to calculate the heat transfer per unit length of that fuel rod. Sometimes we need to calculate the rate of heat transfer, but instead of per unit length, we need to calculate it per unit surface area. So rate of heat transfer per let's give it that way, surface area. Or unit surface area. Unit surface area. Let's remove these parentheses. So up to here, rate of heat transfer, that's the same as the first definition, Q, which has a unit of watts. And now I'm going to get that per unit surface area. So the units would be actually watt per meter square. Okay. Sometimes we call that linear power. Power because it has a unit of watts, and watts is a unit of power. And because it's per unit length, sometimes we call that linear power. This is just an alternative name. And the second one, sometimes we call it the heat flux. Okay, so the word flux usually refer to anything per unit area, right? So you say that magnetic flux is the magnetic field strength divided by surface area. Heat flux, it is the thermal energy per unit surface area. What else? Any word flux in general is dividing that property per surface area. So that's what's going to give you the word flux. Symbol-wise, we call that Q, but instead of having one dash, it's going to be double dash. The last symbol that we're going to calculate here is going to be the rate of heat transfer per unit volume. Okay, and it's clear rate of heat transfer was still with the basic unit watts, and now per unit volume. So the final unit will be actually watt per meter cube. And the equivalent name for that rate of heat transfer per unit volume, we call that actually the heat generation. Or the other name, it's thermal volumetric source strength. These are all names that you're gonna hear along the course. You're gonna see that in a different language in the exercises, the homeworks, the quizzes, and so on. So keep in mind to be aware of the other names or other options that we have for each one of these long terms here. From symbolic perspectives, we give that Q, then they discover that 3 dash is going to be like heavy lifting here. So let's make that much simpler. So they put actually, instead of Q, triple prime, usually we use Q and we put dot here. Dot here doesn't mean rate, it's already rate, but dot here refer to the heat generation term. So either this or this, but we use any one of them, doesn't matter. Again, it depends on the reference you are study from. So these are the quantities that we always need to calculate along the course. We're going to look into Q, Q dash, Q double prime, or Q double dash, and Q dot or Q triple dash. And you can tell they are related, right? If you know the total thermal energy coming out of a nuclear fuel rod, then you divide that by the length, you can get Q dash. If you divide that Q by the surface area, you're going to get Q double dash. If you divide that Q by the volume, you can get Q dot or Q triple dash. So they are really connected. This is the most important one. Then you can, depend on the given information in the problem, you can calculate Q prime, Q double prime, Q triple prime from the known value of Q. So these are the quantities that we're going to calculate along the term. Now, when you look, we need to look into the different mechanisms that energy would transport in nuclear application. And this is still very fundamentals as well, but we need all of them for the course. So let's look to the mechanisms of energy transport. If you have a background of mechanical engineering, if you have background of physics, if you have background of chemistry, I'm sure you have heard about these mechanisms before. The three major mechanisms of energy transfer is the conduction, heat transport or transfer, the second one is the convection, heat transport or transfer, and the third one is radiation, heat transfer. Why we need these three mechanisms? Because the three mechanisms exist in nuclear application. So let's recall that when we look to the fuel rod composition, we used to have the fuel pellets, right? That tiny, small cylinders, and we stack multiple of these pellets over each other, right? So let's assume that we have like three fuel pellets. Then we are having a gap between the fuel pellets and the big container, which is the cladding. Please go back to the original, the first lecture that we introduced the nuclear power system. And that cladding, it's another pipe or tube with a wall thickness, right? So I'm going to assume this is a very short fuel rod or fuel pin here. Okay. And remember that cladding should have a wall thickness here. So I'm going to give it a little bit of a thickness here. Let's add another maybe fuel pellet down there. Okay, so I'm simplifying here the fuel element. So this is your fuel. This is the gas gap. As I mentioned, for light water reactor, it's filled with helium. In some other designs, we fill it with sodium and so on. And this is what we call the clad, right? So let's look to that. You will find that when we talk about the fuel here, all the thermal energy transport in this fuel here has one mechanism. Then energy will transport from the clad through the gas gap with two mechanisms. Then energy will leave the thickness of the clad by one mechanism. Then outside the clad, what do we have? We have the coolant, right? So we need another mechanism for heat to go all the way from here to here. That's the purpose of the reactor, is to transport the energy from the nuclear fuel to the coolant, and this coolant will go to a secondary loop, or maybe it's going to boil and form steam directly. It doesn't matter what the concept is, but this is what we are analyzing: how energy will transfer from the nuclear fuel all the way to the external coolant, and what are the mechanisms of that energy transport between these two spots. And we found that these three mechanisms exist. I'm going to explain briefly each one of these mechanisms, but most of the focus will be actually on the first and the second mechanisms. And third mechanism is more complicated, but it exists, but it's not going to be covered in the course, except just explaining a little bit of the concepts here. So these are the three mechanisms: conduction heat transport, convection heat transport, and radiation heat transport. Now let's start with number one, which is the conduction. I'm just going to write the short name so we can actually save the space here. So conduction means that no motion is involved. Nothing is moving. Okay? So for example, let's assume that you have a source of a fire and you decided to have a metal bar One end is located inside that fire, okay? And the other one is you hold it by your finger. What's going to happen after a minute or two or a few minutes, depending on the material of that bar, how long it is, and so on. We know that after a few minutes, you will start actually feeling heat coming to your hand, right? So the energy will transport, taking that metal rod, that's metal, as a bridge to transfer from the source to the sink, right? And the driving force here is actually this fire has a high temperature, your hand has a low temperature, and due to that temperature difference, energy will transport and it will take that metal rod as a bridge to transfer from one end to the other. So it is very important to have a driving force for energy transport. So if you have delta T, this will allow for thermal energy to transfer. Think about a flow in a pipe. You have a piece of pipe and you want to drive a flow of water into that pipe. What is the driving force? The driving force is to have delta P, a pressure difference between the two ends so you can drive the flow. So delta P will enable the flow, right? Same for the wind. If you want to bring a wind from one location to the other, you need to have a pressure difference, and so on. Think about electric circuit. What do you need to drive an electric current between 2 points? You need to have a potential difference, voltage. So delta V will be the driving force for electric current. So there is always a required delta T. If that a required driving force. If that driving force does not exist, there is no transport. That's a condition for transport. Imagine if this is, the fire has a temperature very similar to your hand, there will not be any thermal energy to transport. If the pressure at this point is the same as the pressure at this point, there is no flow of the liquid. If the potential, the voltage at these two nodes here is the same, there will be no current to go through the resistance. So that's very essential condition that you need for thermal energy to transport. Now, how the energy transported, it went through the metal bars. So we're looking for putting that metal bar under the microscope and see how maybe the mechanism of that energy transport. So I'm going to have a piece of solid, and the only thing I can see under the microscope is actually having the molecules, right? Or particles or atoms. Then I'm heating that phase here. So that's high temperature phase. That's a source. What's going to happen? What's going to happen is I will have a few of these atoms very in contact or intact to the surface. So some of the energy will transfer to these particles or these molecules or these atoms. So these atoms now are carrying energy. But we know that all molecules are always under vibration motion, right? And this is happening at the outer shell of the atom. When you have free electrons, these electrons are free to move, right? So they can actually move, correct? So what's happening is these molecules will vibrate. When they vibrate, they're gonna make a collision and they're gonna transport some of the energy to this one. And this one is gonna make vibration, is gonna transfer by collision some energy here, and so on. The other way is the free electrons in the outer shell will transfer, and these electrons will carry energy to the next one. So we have either the vibration, we are talking about micro scale here under the microscope. These are very tiny, but it's happening. Or looking for free electron transfer. So these are actually explaining how the energy would transfer from one spot to the other, and this will continue until you reach the end here. That's when you start feeling the thermal energy into your hand, either by the vibration of the atoms or the transport of the free electron in the outer shell of each one of these atoms. So that's one way to do that, and this is very common in solids, right? Someone would ask, what about liquids? Does liquids actually can do conduction? And the answer is yes. Let's have a microscopic zoom here. Let's assume this is my liquid. And what's apply for liquid maybe apply for gases too. So let's have them next to each other. So let's assume that I have a certain number of gas molecules and certain number of liquid molecules. We know that the only difference that in the solid, molecules are more closer to each other, right? The intermolecular distance between the molecules or the atoms is very tiny, but these spaces are much larger compared to the solid for the liquids, and for gases, the intermolecular spacing is huge, okay? So the only common parameter here is the intermolecular spacing increase when you go from the solid to the gas. So now, what's going to happen is if you are supplying energy here, that's your source. The molecules that intact to that phase will carry energy. But now we know that there is more freedom for the molecules to move in the liquid. So what's going to happen is these particles will carry energy and they will be more energetic. They will get kinetic energy, so they're going to transport. And this molecule will be transport. While it's transporting, maybe make a collision. It's going to put some energy here. This will become more energetic. It's going to start moving. So we call the actually diffusion of energy carried by the molecules or the atoms due to the more freedom of the particles to move. So we call the actually diffusion by collision. These collisions still exist in the solid material, but it's very restricted because they are not allowed to move. Particles in solids, they don't have the freedom to move or diffuse, but they have a freedom to vibrate or rotate in their location. So that tiny vibration and that rotation, it's what's making tiny collisions. So the dominant mechanism of energy transfer in the solid is not really the motion of the particle, but it's more the free electron transport and a little bit of vibration. But they don't have diffusion. They cannot move, right? They move actually a long period of time, over a long period of time, but we're looking for classical study. We're not looking for hundreds of years to see the molecules of the glass go from the top to the bottom, right? This is a very common problem here. Going to the liquid or liquids have more freedom for their atoms or molecules to move, so they will diffuse, they will carry energy, and the molecule will move from one location to the other. It's going to make a collision. During that collision, he will transport some of the energy to the next one, and so on. So diffusion is the dominant one. For gases, the freedom is higher, which means that diffusion actually is higher. So in gases also we have diffusion and collision. So the mechanism for liquid and gas is almost the same. Molecules that receives energy from the source here. Then I have particles that intact with that surface here. They will become very energetic. They're gonna start run. They're gonna make a collision. During the collision, will charge these particles. This particle will start move and so on. But the probability of collision is less compared to the liquid, right? So that's why gases takes longer time to conduct or to move heat by conduction. So these are the mechanisms of conduction. Mechanisms of conduction. So we break down the heat transfer mechanisms into conduction, convection, and radiation. Now we break down the conduction mechanism either by vibration or free electron transport in solids, or diffusion mostly in liquids and gases. So how we analyze that energy transfer, how we calculate it, again, we're looking for numbers here. So the equation that control the calculation for conduction, it's called actually Fourier's law. And Fourier's law is how to calculate, is give you the formula to calculate the heat transfer in a solid material. The general form of the equation is Q. Remember, we're looking for Q, Q dash, Q double dash, or Q triple dash, or Q dot, can be calculated from minus K A partial T by partial X. In some other forms, I can say minus K A dt by dx. Okay, so that's the general form of Fourier's law. Again, Q is the heat transfer rate and has a unit of watts. K is known as the thermal conductivity, and this is a material property, which means that if I look, for example, K for copper is about 400 watt per meter Kelvin. If you look for water or look for gas, K for helium is about 1 watt per meter Kelvin. And now we understand that solids, because of that smaller intermolecular distance here, they can allow for more energy transfer. So thermal conductivity is, in a simple language, is the ability of material to conduct heat. So it's clear from this discussion here that K for solids are expected to be larger than thermal conductivity of liquids and expected to be greater than the thermal conductivity of gases. So that's from the mechanism of conduction itself. What else? We need to continue to define the parameters of the equation. So we have A is the area, so has a unit of meter square. And in conduction, this is the area that has a perpendicular orientation to the direction of Q. This is very important. We're going to talk about this. So they have to be perpendicular. So you look the direction of Q, and you look to the area that's perpendicular to that Q, or the direction of the heat transfer, then you calculate the area for this equation. Then the last term is dt by dx, or partial T by partial X. This is called the temperature gradient. Okay, so how we simplify the use of Fourier's law? Let me draw a schematic here to explain Fourier's law. Let's assume that we have a cubical shape here, and that's made of solids, solid material. So that's, let me actually adjust this. So we have here a 3-dimension body. Let's assume that that back face in the back has a high temperature, and that front face here has a low temperature. Then let's assume that everything else is isolated. So there is no chance for heat to come out of this face, or that bottom face, or that front face, or that back face. It's only going to transport between the back and the front face. We simplify that drawing by 2-dimension lines here. So there's 2 lines, as if I'm taking the projection of that body here. So I'm going to see that thickness here. You don't have to draw the upper and lower end lines here. So that line here is the projection of that back face. So I'm going to write here TH. And that line here is presenting the projection of that face here. I'm going to call that TL. And you will realize that I wrote TH higher than TL. That indicates that that face has a higher temperature compared to that face. This is the thickness of that wall here. I'm going to call that L, which can be transferred into that 2-dimension drawing as L. Remember, this is a projection of XYZ body, right? So we are dealing with X, Y, and Z. This is Cartesian coordinate. It ends up to be like this. What about if we have cylinder? Okay. If you get the projection of the cylinder, you will see it the same way, but we have different equation to use. Okay. So just let's keep in mind that we are dealing now with Cartesian coordinate. To distinguish that, I'm going to say there is an x-axis that starts from here and going that direction. Okay, so at the beginning of that thickness here, this is where x equal 0, and this line here is at x equal L. Okay, so number one, this is a high temperature side, this is a low temperature side. The heat has to go in this direction. That's Q. And this is within a solid body, so I know that I'm having conduction. That's going from this face to this face, okay? So this is Q. Let me write down the equation again. Q is equal minus K A dt by dx. That's the Fourier's law for conduction, okay? I forget to mention here, dt by dx has a unit of what? This is partial t by partial x. This is delta t over delta x. So it could be Kelvin per meter or degree C per meter. Why it's Kelvin or degree C? Because it's delta T. And we did explain on the temperature scale that delta T on Kelvin scale is the same as delta T on Celsius scale. So it doesn't matter here. So let's see how we're going to use this equation to calculate the quantity of Q. Q is the quantity of heat going from that phase to that phase. K, it's a property of that material. So if this is copper, K is going to be like 400. If this is steel, I can go open any table and get the value of that thermal conductivity. So K is known based on the material. Q is what I need to calculate. Now, what is A? Again, A is defined as the area perpendicular to the direction of heat. Heat is coming that way, from the back face to the front face, right? What is A we are talking about? This is the area I'm talking about. This is A, which you cannot see that area on this projected two-dimension drawing. So area is hidden. It's the one inside the page. So keep that in mind. So that's what A is, okay? Which cannot be L times that height. No, it is calculated from the depth times the height. Please be careful with that. Okay, so then what's dt by dx? dt by dx is temperature gradient. It's the first derivative of temperature as a function of x. So my question is, what's happening to the temperature as you go from this phase to this phase? Temperature goes down, right? This is high temperature, this is low temperature. So the temperature goes down. So now, if I assume temperature will change like this, so T is decreasing as X increasing. X equals 0 for this line, X equal L. So the more you go into the X direction, the temperature goes down. So the change of temperature relative to the X is decreasing, and that's explain that negative sign here. So because dt by dx is going down, the slope of that temperature curve is negative, okay? That's explained. So how we're going to use this equation to solve that problem? So far, I can't unless if I know t as a function of x. Then I can take the first derivative, dt by dx, then I'm going to substitute into the equation, right? And this will happen in advanced class within that course. But so far, we don't know what is the temperature function as a function of x. So the first assumption that we're going to use is dt by dx is slope of a line, which means that we will assume temperature change linearly as I draw it here as a straight line with the position x. So now, if you want to get dt by dx, which is the slope of this line, right? How to get the slope of that line here? You can get that difference here. That's delta t. And this part here is delta x. It's going to give you the angle here, right? But we know the slope is not this angle. The slope is this angle, right? And that's where that minus is going to help us to do. So the simple form of Fourier's law to use is Q equal, I will remove the minus now. I will keep it, let's keep it that way. K A, right? I need to get the slope here. So it's going to be actually TL minus TH divided by the thickness L. That negative will change that here. So the final form of the equation will be K A delta T, TH minus TL divided by the thickness L, which is that slope, and that negative sign switched the slope to give me the actual slope here. So delta T over that thickness, which is L. And this is the simplest form of Fourier's law to use when you have a Cartesian coordinate like this, and it's actually for plane wall. So this is, we call that plane wall, which means that it is defined by X, Y, Z, or Cartesian coordinates. What if we have a cylinder like this? What if we have it like this? This cylinder, if you take the projection, it's going to be very similar here. So Fourier's law for this cylinder should be written as minus K A partial T by partial R, whereas R is the coordinate measured from the center line all the way to the outside. The big radius here, we call it R capital, but the R here is the variable R, like the variable X. So X changed from 0 to L, R changed from 0 to R capital. Now, this is the Fourier's law for cylindrical problem. Even they're gonna look like the same when you take the projection, but be careful if you are solving cylindrical shape originally, you have to use this equation. How we're gonna simplify partial T by partial R? There is no way to assume it's linear. We know it's not linear. We're gonna talk about this later, but I cannot use this for this. Cannot be used for cylinder. So please be careful, because sometimes students get confused when they see the two-dimension problem. That's, if I take the projection, it's gonna look like this. This is very rough assumption, and it's gonna give you a lot of errors. So keep in mind that we cannot use this equation for cylinder. We're gonna talk about this later on. It's a quick assumption, but it's highly uncertain, and it has a lot of error into it. So we're gonna talk about this later on. So this is what I'm gonna use if I know the temperature distribution as a function of X, or I'm going to use this equation for plane wall conduction heat transfer. Okay. What else? I can now put this equation here or this equation here. Can you calculate, for example, Q double prime? Yes, let's take that equation here. If I divide both sides, Q over A and K A T high minus TL over L divided by A. So I divided both sides by A. What's going to happen? This will cancel out. So the left-hand side here is Q double dash. So Q double dash can be simply calculated from K delta T over L, or TH minus T low divided by L. So you remember I told you, if you know what's Q, you can divide by the length. You got Q dash, you divide by the area, you can get Q double prime, which is the heat flux. You divide by the volume, you can get Q triple prime, and so on. So this is just to show you how to use the equation for driving other variables that we may need to calculate. Okay. Let me clarify one thing here. Does it have to be a vertical wall like that? No. Let me show another example here. So let's assume I have a bar, looks like this. That's a metal bar. And I am keeping that front face at high temperature, that back face at low temperature. Then I'm isolating all the other sides, which means that heat, let's assume this is 100 degrees C. Let's assume this is 20 degrees C. Now I'm sure there is heat will be conducted from here to here, through along the length of this guy here, which has a length of L. So now I want to calculate how much Q is going to move from that face to that face, assuming the other faces are isolated. I will simply use the equation Q is equal to K, which is dependent on what material this is, then A times TH minus TL divided by the length. Remember, L is always the distance between that face and that face. L is distance between faces TH and TL. Okay, so that's the length here. So if I'm looking for the heat from the bottom to the top, the length will be the thickness, and so on. Okay, but what is A? The area I'm looking for is the area that's perpendicular for the heat transfer, right? Which is this area here. This is the area I'm looking for. So now I can apply the equation and use it. So let me give you a tricky idea here. What about cylinder like this? If you're looking for the heat going from the center line to the outside, this equation does not apply. I have to use the equation with partial T by partial R. But what if I told you that face has a temperature of 100 degrees C and that face has a temperature of 20? What is the direction of heat? Heat will go linearly like this. Now it doesn't matter. I'm dealing with the same case here. That's Q. So how are you going to use the equation? Q is going to equal, what is K of that material? Km. What is the area perpendicular to the heat? Is going to be a circle. This is the area I'm looking for. So the area is going to be circle. What's the area of a circle? Pi r squared. What is r? Is that radius here? Let's make the r capital. Or if I know the diameter, say that's d capital, it's going to be pi g squared over 4. Any one of them will give you the area of a circle. Then you take T high, which is this face temperature, T low, divided by the distance between these two faces, which is going to be the length of that cylinder L. Now you can use the same equation here to calculate. So be careful. Cylinder sometimes is confusing, but you should be very cautious when you use which direction of the heat we are looking for, and so on. So I hope that gave you a good idea about what we call the conduction heat transfer. Now let's move to the next mechanism of energy transport, which is convection heat transport or transfer. Remember when we talked about conduction, we said almost there is no motion, right? So even when we explain the conduction in solid, liquid, and gases, we talk about stagnant fluid, solid, stagnant liquid, or stagnant gas. They are not moving. But we know that even if the liquid is stagnant or the gas is stagnant, the molecules are not. They are moving, right? So you put some water in a cup. This is a stationary water, but we know the molecules are not stationary. They are in a motion all the time. Now, when we move to the convection, now we're looking for motion. So convection is always associated with motion. What does that mean? It means that solids are excluded. So I cannot use just, I have a solid that doing convection heat transfer itself, unless I actually melt it down, like with liquid metals, okay? But usually there is a fluid motion involved. What does the word fluid mean? The word fluid is a combination of liquids and gases. As soon as you see fluid means liquid or gas involved in the process of heat transfer, we are looking for, and this fluid is in what? Is in motion. We consider convection mechanism. So for example, if I go back to the fuel rod here, there are two fluids in this example here. There is a gas gap, which is usually filled with helium, and there is a fluid outside. the helium gas gap is not in a motion. It's stationary. So I'm still looking for actually conduction through that helium layer. When I look to the coolant outside is in a motion, which means that convection is existing outside here. What about the mechanism for the fuel pellets itself? Correct, it's conduction, it's a solid. So I have a conduction in the fuel pellets, followed by a conduction in the helium gas gap, followed by a conduction in the thickness of the clad material. These are all either solids or stationary liquids or gases. Then heat will move outside that fuel rod or fuel pin by a convection. Why? Because there is a coolant, liquid or gas, right? Light water reactor, that's a water. Sodium cooled reactor, that's a sodium or a lead. Molten salt, that's FLiBe or chloride salts. That's a gas cooled reactor, that's helium as well outside, but all in motion. So now convection will be associated here. So keep that in mind. Convection is associated with the presence of a fluid in emotion. That's very important. Very simple example to explain that convection mechanism here. Think about boiled egg. And you put that boiled egg on a table. So the boiled egg has hot surface. Then I'm going to open a fan to drive air, which is usually cold air. So it's going to be at lower temperature. And that air will go over the egg. What's going to happen? A cold air touching a hot surface, then heat will go out or energy will transfer out. That's why the boiled egg will cool down. This is Q. Okay, now Q will transfer from a solid surface to a fluid, which is gas in this case, which is air in emotion. So we know that Q will go by convection mechanism because I have a moving fluid involved in. Okay, that's very important. The other way, I will have the same boiled egg that's hot, has a high surface temperature, T high, sitting on a table. But instead of actually running a fan to cool it down, I'm going to stand up next to the boiled egg and I'm going to blow up air from my mouth to cool it down. Again, that's gas, air, and it has a lower temperature. I'm expecting a transport of energy from the boiled egg. Even it's going to take longer, but it's going to happen. And that Q will be convection as well. So both are convection mechanisms. The first one, we call that actually what? We call that, let me use a different color here, forced convection. The lower one is called natural convection. The first one is called forced convection because we are forcing the air to go over the egg because of that fan. So that fan is what made it actually a forced convection. There is no any mechanical component involved. That's called natural convection. So keep that in mind. There are two types of convection. The first one is forced convection when mechanical device is used, fan, pump, blower, which is true in our case when we talk about the nuclear reactor, because we know that the coolant that circulated in the reactor core is driven by a pump. If we talk about liquid, metal, molten salt, or actually water, right? Or it's a blower that's blowing up the helium for the gas-cooled reactors. So either we are using any mechanical component that's called forced convection or not, so we are called that natural convection. So these are the types of convection heat transfer. So in both cases, again, forced convection, let me write it down. We have fans, pumps are involved in the process. There is always a mechanical component involved in the process. So now, how are we going to calculate that Q, and what is the equation that we're going to use for that calculation? So the equation to use for calculating Q, it's called actually Newton's law of cooling. Newton's law of cooling. And it states that Q, which is the heat transfer by convection, is equal H AS TH minus TL. Again, this is the driving force. That's delta T. Without that delta T, there is no energy transfer. AS is the surface area. That's different than the conduction. Conduction, it was the area that's perpendicular to the heat transfer. Now, this is a surface area. The boiled egg will cool down from the outer surface. So that's a surface area, okay? And H is known as the convection heat transfer coefficient. The unit of the surface area is meter square. Again, I'm simplifying by using the SI unit. The convection heat transfer coefficient, you can get the units from here. This has a unit of watts. This has a unit of meter square. What's the unit of delta T? Kelvin or degree C? Go back to the temperature scale. So if you want to get the units of H, it's going to be watt divided by meter square Kelvin. So it's watt per meter square Kelvin or degree C. It doesn't matter. It's coming from delta T. And what is H? Is a property of the fluid. So it's a specific property. It's a thermophysical property. Thermophysical property of the fluid, which means that there is no H for copper. There is no H for aluminum. There is no H for wood. There is no H for any solid material. But H is only for fluids. So you will find that there is H for water. There is H for air. There is H for helium, and so on. Now, if I'm cooling down a boiled egg using water, and I'm cooling down the same boiled egg with air, which one is going to cool down quicker? If you dump that boiled egg into a water bath and the other egg into the air atmosphere, which one is going to cool down faster? The one in liquid. So we are expecting that H for liquids is going to be higher than H for gases. And again, H is tabulated value. We have tables. That's why we like to cool down the light water reactor with water, because water is a liquid, has a higher potential convection heat transfer coefficient, right? Helium is the worst one, okay? But we can compensate that by some other ways. I'm going to talk about this later on. But I hope that's now, guys, you get the idea about the convection. So let's take an example quick example here. Let's assume that I'm having a cylinder or a sphere. I'm trying to get a drawing of reasonable sphere, okay? And the surface TS, the surface is TS. Then I want to cool down either that cylinder or that sphere quickly. So I'm going to blow up fluid, which means that could be liquid, could be gas. And that fluid is at lower temperature. Usually, the fluid temperature take the symbol of subscript infinity. It's not a value, it's just a symbol. So the fluid temperature usually called infinity. So this will be always called T infinity. So that fluid is at T infinity. So when you see the subscript infinity, you know that we are talking about what? About a fluid, liquid or gas. Okay? Now, we know that that fluid is colder than that surface. It could be the opposite, by the way. So the direction of the heat transfer is going to depend on which one has a higher temperature. And this here is delta T. We're looking always for the difference. So don't care about the sign here, okay? So how are we going to calculate Q going out or going into that face, or Q that's going out or going in? Again, the direction will be determined by which one has a higher value. So Q for that face, for that cylinder is going to be actually H of that fluid. I will call it HF. Then time the surface area times delta T. Delta T could be T infinity minus T surface, or could be T surface minus T infinity. I don't care about the sign here. I care about the difference. That's the same apply for this one, okay? H of the fluid, surface area of the sphere times delta T, depending on which one is greater than the one. What is the surface area of a cylinder? If the cylinder has a diameter D and length L, what is the surface area? It's pi times D times L. What about the sphere? Surface area of a sphere is 4 pi r squared, whereas r is the radius of that sphere. Correct? Now, I can substitute into this equation, I can calculate Q. You will realize that only for cylinders, there is what? There is L, length, right? So if you write the equation for a cylinder, it's going to be HF pi dl delta T. If you divide both sides by L, what you're going to get? I'm going to get Q dash equal HF times pi times D times delta T. There is no any other surface area that has L into it except cylinder. So Q dash always needed for cylinder geometry. Just keep that in mind. If I divide it by surface area total, I will get Q double prime, right? It doesn't matter. There is no L here. You can, it has to be the length, linear length, right? You cannot say I'm going to divide by R. R has a unit of length. No, you need a linear length, okay, to get the heat transfer per unit length. Sphere doesn't have a unit length, right? So that should be the all what we need to learn or to fresh our memory with the convection heat transfer.